All right, welcome everyone to the AATRN seminar today. Our speaker is Shreyas Samaga, who will be talking about Quasi Zigzag Persistence, a topological framework for analyzing time-varying data. Floor is yours.
All right. Thank you, Bastian. And firstly, I would like to thank the organizers of AITRN for giving me this opportunity to present my work. So today I'll be presenting one of our recent works, Quasi Zigzag Persistence, a topological framework for analyzing time-varying data. This is joint work with my advisor, Professor Tamal Dey at Purdue University. So what I'll do is I'll kind of set the context and the motivation for the talk in the first few minutes, and then we'll get into the details of the framework. Okay, so just to make sure the laser pointer is still visible, right? Okay,
Yes,
cool.
it is.
All right. Yeah. So, okay, let us begin by understanding what we actually mean by time varying data. So, time varying data can occur in multiple forms. For example, a multivariate time series data is an example. Then we might also have something in the form of a sequence of point clouds. So, here, if you see, the bottom row of this cartoon is showing a man doing a tennis serve or a person doing a tennis serve, and we have snapshots of the position of the person's hands at different timestamps, and we this is kind of like a sequence of point clouds. And on the top row, you see a person drawing a tick mark. So this is again like again can be captured as a sequence of point clouds. So this is also a form of time varying data that we consider. And there's one more form, which is a sequence of graphs. So let's say a network evolution process. This can be any sort of a network, like a biological network, or maybe even like a social network, to see how it kind of evolves. So like a sequence of graphs. So we have multivariate time series, we have a sequence of point clouds, we have a sequence of graphs. So these are the kind of time varying data that we are looking to analyze. And in the machine learning literature, there are multiple methods to oh, sorry, yeah. There are in the machine learning literature, there are multiple methods to kind of analyze these kinds of data. So, for example, there are methods for multivariate time series. Then, for the sequence of graphs, there are these things called spatiotemporal graph neural networks. So, these are essentially a form of the regular GNNs, but here there are like two different modules. One module models the spatial dependency in the data, and the other module kind of models the temporal dependency. So the spatio-temporal dynamics can be captured. And then we also have this a similar kind of architecture for a sequence of point clouds. These are called PST nets. Uh, so one thing that we noticed is that uh, currently, like, there is no kind of way to capture the topology of the evolution of these data. So what I mean by that is like a global pattern in the topology. So for example, in the cartoon that we saw in the sequence of point clouds, if I were to distinguish between a man performing a tennis serve and a man drawing a tick mark, how do I capture the topology of this evolution? So in order to answer that question, we came up with the topological framework that we introduce in a bit. Before we get to the framework, I'll just have a quick recap of the required concepts in persistent homology. I don't think I need to go over this because I'm assuming the audience already knows this, but for the sake of completeness, let me quickly go over it. So, one parameter persistent homology, we start with a nested sequence of simplicial complexes, and then we consider the homology of each of these complexes, and the inclusion induces a linear map on the level of homology, and we track the homology of through this sequence. And this can be compactly summarized as barcodes. And this diagram does a very good job where you can kind of see. So this is a feature born at this time, and then there's like a bar that starts here, the green one, and then it ends here, where you see that this feature is still alive at this point, but it kind of ceases to exist at this point. So the bar kind of doesn't pass that stage. All right. So with this, the next thing is how has standard persistent homology been used in machine learning? So there are certain ways of vectorizing a barcode or a persistence diagram. So what we mean by that is we convert the topological information summarized in the barcodes into a vector, and we use it for different machine learning purposes. So there are multiple ways to vectorize a persistence diagram. I've just mentioned a couple here. Mm. All right, so this was one parameter persistence. Um, what about generalizations of persistence? So one thing that kind of naturally comes to my mind is multi-parameter persistence, where we not only have just one scale parameter, we have another parameter that we want to kind of vary and see how it changes the topology of the simplicial complex. So we get like a grid of simplicial complexes. This is one generalization. The other generalization that I can think of is zigzag persistence. So in zigzag persistence, it's not necessary that the inclusions are all in the same direction. So we can have inclusions going in the opposite direction, which is equivalent to saying that we are deleting a simplex from the simplicial complex. So zigzag, what this means is zigzag persistence offers the flexibility to track the deletion of a simplex as well, along with the addition. And it is known that zigzag persistence modules also decompose into a sum of interval modules uniquely up to reordering. And this is a consequence of Gabriel's theorem on QoR representations. And since they also decompose into barcodes, we have a corresponding persistence diagram, and then the same kind of vectorization schemes can be used for zigzag persistence, for zigzag persistence to be used in machine learning. But what about multi-parameter persistence, right? So Carlson and Zomorodian in 2009, they kind of showed a result that is not that's not very friendly in some sense for capturing the complete summary of multi-parameter persistence modules. But so this is a typical bifiltration that I've shown in the grid here. And if we consider like the homology of each of the simplicial complexes, then we get like what we call a multi-parameter persistence module. And the theorem that they showed is is that a multi-parameter persistence module cannot be completely characterized by a discrete invariant. So what that means is there is no barcode equivalent. Here, by barcode equivalent, I mean a complete summary of the information in the multi-parameter persistence module. So there's no complete summary, and hence this naturally leads to the question how to capture the topological information of a multi-parameter persistence module, right? And in this direction, there have been multiple works that kind of vectorize a multi-parameter persistence module directly. So there's multi-parameter persistence kernel, there's multi-parameter persistence image, then there is multi-parameter persistence landscapes, then there's this thing called generalized rank invariant landscapes, and then we have signed barcodes as measures, and also graph codes, which came out like in sometime last year. So these methods that are kind of ways to vectorize a multi-parameter persistence module directly. All right. So with this context and with the context set, let us come back to the main question that we started with, right? A topological framework for analyzing time varying or spatiotemporal data. So the moment I think of time varying data, the thing that kind of comes to my mind is zigzag persistence, because zigzag persistence allows us the flexibility to delete simplices. So, for example, in let's say a social network, how a social network evolves. Two people that are friends today might not be friends tomorrow. So we might need to remove the edge between those friends, and then they might again become friends sometime later in the future where you need to add it back. So in order to kind of model this kind of phenomenon, uh, zigzag persistence is like a very nice tool to do that. Uh, so zigzag persistence naturally comes to mind. The other thing is, since we also care about the spatial dependency in the data, we need another parameter along with the time being one parameter. In the spatial coordinate, we need another parameter which gets multi-parameter persistence into play. And the framework that we propose is called Quasi Zigzag Persistence, which is a confluence of both these kind of approaches. So it multi-parameter persistence and zigzag persistence together kind of combine to form Quasi Zigzag Persistence. Uh, all right. So okay, let's delve into Quasi Zigzag Persistence more. The thing that is underlying any filtration is a poset, right? A partially ordered set. So what would the poset look like for a quasi zigzag persistence? So consider let ZZ denote the alternating zigzag poset, and Z denote the irregular poset for integers. Then a quasi zigzag poset is any subposet of the product of ZZ times Z. Uh, what this means is this is how a typical quasi zigzag bifiltration would look like. So here, if you notice, each horizontal filtration is a zigzag filtration, and each vertical filtration is a standard filtration. So again, very similar to a two-parameter persistence module where the inclusions are all in the same direction. Here, the inclusions in the horizontal direction are inclusions in the horizontal direction are reversed, but inclusions in the vertical remain the same. And hence the name quasi zigzag, because it's only zigzagging in one of the directions. In the other direction, it's a standard filtration. All right. So once we have defined a quasi-zigzag bifiltration, the next thing is a quasi-zigzag persistence module. So we apply homology to the uh, bifiltration, and that gives us a quasi-zigzag persistence module. So for example, here, if we track the H0 of each of the simplicial complexes in the bifiltration, then we get the persistence module that is shown on the right. Here, so as you can see, there are like two connected components, and then there's like two copies of the field. Here there are four in the middle, and then so on. So this is how a typical quasi-zigzag persistence module would look like. All right. So this again gets us back to the same question that we had when we were thinking of how to extract information from a multi-parameter persistence module, right? Because this also looks very similar to a two-parameter persistence module, except that it's zigzagging in one direction. But the question is still the same as to how does one kind of extract the topological information from this kind of and this kind of an algebraic object. And that gets us to uh, ZZ grill or zigzag grill. In 2023, in a joint work with Cheng Xin, Soham Mukherjee, and Tamal De, we proposed a vectorization scheme for two parameter persistence modules, which we called grill, because it's a landscape function based on the idea of generalized rank invariant that Bujin, Kim, and Facundo Memoli proposed in 2021. So here we propose a similar vectorization scheme for vectorizing a quasi-zigzag persistence module. So what I mean by that is we want to capture the topological information in the module and summarize it as a vector that we can use for further machine learning purposes. Okay, so to kind of understand what ZZ Grill is, let us begin by the definition of generalized rank. So given a persistence module on a finite and connected poset, the generalized rank of M over a subposet I is the rank of the canonical limit to colimit map, rest of the module restricted to the subposet I. So what we mean by this is, so consider this example here, right? So here, let's focus on the blue rectangle in the bottom. So this is a subposet of the big poset shown in green. And if we focus on this, then the rank of the map from the limit to colimit. So here the limit would be this point on in the bottom left, and the colimit would be this point in the bottom right. So the rank of the map from the limit to colimit would be 3 in this case, right? Similarly, if we were to focus on this yellow rectangle or the yellow subposet, then the rank of the limit to colimit map in this case would be 2, because limit is this is the limit of this subposet, and then this is the colimit. So of the module restricted to the subposet. So therefore, the rank of the limit to colimit map would be 2. However, it is not necessary that we consider subposets that only look like rectangles. We can also consider an arbitrary subposet that looks like this purple thing, purple shape shown on the right. Yeah, and one can kind of define the same concept for any such subposet. And one more kind of useful or important property that we will need is the fact that so generalized rank has this property called the monotone property. So what it means is if we have two subposets I, which is contained in J, then the rank over I will be greater than or equal to rank over J, which means so for an example, we can consider this yellow subposet again and the green subposet, the big one, like the entire poset. So the rank over the entire poset, as you can see, is 1, but the rank over the smaller poset is 2. What this means is that as the poset kind of keeps expanding, the rank over it keeps dropping. So we this is a property that we kind of need, and we'll use this property for defining grill, ZZ grill. Okay, so we define these special kind of special looking subposets or a particular shape of subposets, which we call worms. So let P delta denote the P center delta square, where P is a point in ZZ times C. Then a worm is the union of two delta squares that are on the off diagonal. So what I mean by that is this. So the central square here is the P delta square. And then the two squares that are centered on the off diagonal are the one on the top left here and the one on the bottom right here. So this shape forms a worm. Uh, So this is very much this is very similar to the definition of worms that we had in the grill paper. Uh, yeah, so this is kind of the analogy. And then with this, we are ready to define ZZ grill. So ZZ grill, let M denote a quasi zigzag persistence module. Then the function ZZ grill is defined as a function from ZZ times Z times n, which is so it takes in a point in the poset ZZ times Z, and then it takes the value of a rank k from the set of natural numbers, and then it spits out a value that is again a value in the natural numbers, right? So what does this do? So what we do is we consider a worm, right? And we keep expanding the worm until the rank over the worm drops below k. So the maximum width of the worm that we can expand it to until the rank drops, until the rank is at least k, is the value of ZZ grill. So here is kind of an illustration. So the worm shown inside is kind of being expanded to the worm shown outside. And then, and as we saw, due to the monotone property of generalized rank, the value of rank over the larger worm would be smaller. So if it drops below k at that point, then we would consider the expansion just before that to be the value of grill. So it is kind of like the supremum over the widths of the worm, such that the rank over that specific subposet is at least k. Uh, okay, so with this defined, we also kind of show that grill is ZZ grill is stable. So there's a notion of proximity on the space of zigzag modules called the interleaving distance. And we extend this definition to quasi zigzag modules. And we show that ZZ grill is stable with respect to this distance. Okay, so with the definition underway, let us now kind of look at the algorithm to compute ZZ grill. Okay, so there's a lot of things in this diagram. Let's unpack them one by one. So we have a bifiltration, that quasi zigzag bifiltration, that is shown in the by the red simplices. And then we have a worm that is shaded in blue. So that is the worm that is shaded. And we can also kind of see the boundary of the worm. So these are the concepts that we'll kind of need to understand how do we compute Grail. So in a paper in 2024, Kim and Memoli, they showed that in the case of a two-parameter persistence module, the value of generalized rank over an interval, which would look very similar in a two-parameter case, can just be computed by counting the number of full bars along the boundary of the worm. But unfortunately, that result cannot directly be applied to quasi zigzag poset because it was very specifically true for a two-parameter poset where the arrows inclusion is all in the same direction. But we leverage certain concepts from category theory, particularly the concepts of initial and terminal functors, and we extend that result to quasi-zigzag poset. So what we show is that even in the case of a quasi-zigzag poset, the generalized rank of the module restricted to a certain subposet can be computed by counting the number of full bars on in the zigzag along the boundary of that subposet. So let us kind of understand what this means and just kind of look at a big general idea of the proof. So what this means is that the part shown in orange along the boundary, uh, we can compute the number of full bars in the zigzag filtration that arises when we traverse along the boundary through along the orange path and which ends here in the top right corner. Yeah. So the proof is as follows. So these points that I've shown in green, the green dots, those are like the local minima of this subposet. Uh, and then the points that I've shown in purple are the local maxima. So, and this green path here is called a lower fence, and the purple path is called an upper fence. So, what the theorem actually is saying is that we consider a path in the subposet that connects the lower fence to the upper fence, then then the value of generalized rank would be equal to the number of full bars along the zigzag if we traverse this path that connects the lower fence to the upper fence. So that is the reason why we start the path from here, bottom right, and continue until here. So the path should have the lower fence, the upper fence, and a path connecting them. That's kind of like the idea. So in the case of regular two-parameter persistence, if you remember, then the path started at this point and ended at this point, because in the case of a two-parameter persistence module, this would also constitute a local maxima. But the local maxima are kind of different for different posets. So that's why this specific path here. Okay, so let us now look at. So this was a theorem on using existing zigzag algorithms to compute the number of compute the generalized rank. So the algorithm is not very difficult. It's like a binary search. So what we do is we do a binary search over all the possible widths for a specific verb. So we compute the generalized rank at a certain value of width, and then we compare it with the value of k that we have. If the value of rank is greater, then we search in this half. Otherwise, we search in the other half. So that is kind of how we get to the actual value of the ZZ function at that point. But one thing this algorithm here we assumed was that we are given a bifiltration function, right? But what does the typical input for us look like? It is a sequence of graphs or a sequence of point clouds. So we also kind of need to build a bifiltration out of this and then use this framework to kind of capture the information there, right? So one way to do that is we consider the union of consecutive graphs, and we build a big zigzag. And from this, we can now build the bifiltration. Let's say one could consider the sub-level set filtration. So let's kind of understand this a little bit here. The ZL, the top portion, is this zigzag that we build out of the given input to us, right? And then now we also, in order to kind of do this computation, we would need to store this bifiltration in a certain way, right? So, I mean, one obvious way is just store the simplicial complex that is present at each grid point, but that would be very expensive. And if we kind of think for a moment as to what is the actual kind of piece of information that we want from this bifiltration, it's primarily the fact that what are the simplices that go along each arrows when we build the zigzag filtration along the boundary of any worm, right? So if we kind of get access to that information, it is sufficient for us because we can sufficient for us to compute the ZZ grid. And it's also an alternate way of storing the bifiltration where you just kind of store the number of the simplices that get included or deleted along each arrow. So there again, we propose like an efficient way to do this without storing explicit simplicial complexes. And we just store which simplices are added and which simplices are deleted along which arrows in a using a certain trick. And yeah, so that's a way to build the bifiltration function. Okay, so with this, so we in what have we seen? We saw what is ZZ and then we saw how to compute ZZ. Now, let us turn to the experimental part where we validate this on some real world data sets. Okay, so let us look at the experimental setup. So for most of our data sets, we considered multivariate time series data. So given a multivariate time series data, we create either a sequence of graphs out of it, or we create a sequence of point clouds, and then we form the bifiltration function. Sorry, we form the bifiltration. And from this bifiltration, we extract the ZZ vector and we feed it to the classifier. In a parallel pipeline, there are existing machine learning techniques to deal with multivariate time series data, and which also kind of presents a representation of this representation vector for the data. And we use GRIL in conjunction with existing machine learning models to feed it into the classifier finally. So let us now focus on this part of the experimental setup where we convert a multivariate time series into either a sequence of graphs or a sequence of point clouds. So let me first begin by describing how we convert it into a sequence of graphs. What we do is we splice the time series into multiple windows with a certain overlap. And in each spliced window, we look at the time series and we compute the Pearson correlation coefficient between the time series. And we draw an edge between two time series if the correlation coefficient is above a certain threshold. So essentially, this sequence of graphs, what it would model is how does the correlation of time series change across windows. So how is the shape of this correlation changing? So this is a way to model the time series as a sequence of graphs. The other way that we consider is modeling it as a sequence of point clouds. This is very similar to Takens embedding, where we consider a spliced time series, and each time series becomes a point in W-dimensional Euclidean space. And the way to get a filtration out of this is either an alpha filtration or a Rips filtration or anything. So there are these two alternate approaches to convert a time series data into either a sequence of graphs or a sequence of point clouds. Okay, so let us now look at some experimental results. So here, what we do is so these data sets are multivariate time series classification data sets, and they're quite well known in the multivariate time series classification community. So we tested our method on the benchmark for this. So we see here that ZZ performs comparably with existing methods on these data sets. However, here one thing to note is that ZZ is a general framework, and these machine learning models are specifically tailored to suit this kind of a setting, while ZZ there's no kind of tailoring that is required to apply to a data like this. So, and the other uh, point that we want to make is that augmenting existing machine learning models with ZZ almost always leads to an increase in performance, which kind of hints at the fact that ZZ is capturing complementary information as opposed to what the existing machine learning models are capturing. So what we are saying is you use ZZ in conjunction to obtain like the best kind of model. Then this experiment is more like an ablation, but it provides some decent good insights into the whole framework. So here we tested the fact that why do we need like a two parameter setup at all? Why can't we just use just one parameter zigzag and capture the information? So here what we do is we capture zigzag information at different scales. So by scale, what I mean is if I were to go back to this slide, so these are the different levels or the scales. So L equal to 5 is the topmost level, and then we kind of keep decreasing it. So since the values are normalized between 0 and 1, uh, of- we compute zigzag at different scales. So zigzag full graph is the topmost level, and then yeah. So here also we see that having like a two parameter setup is leading to an increase in performance, which makes the case for analyzing the whole quasi zigzag module as a whole. Then we compared and contrasted the two approaches that we talked about for converting ZZ Grill into a multivariate time series as a sequence of point clouds or graphs. And from the results, we see that there's no clear winner over the other. So which means that both of these methods are feasible and they kind of offer the same utility, at least with respect to the performance. Then there's this other experiment that we did where so now in the previous ablation study we studied why do we need the two parameter setup, where why do we need the spatial information at all. Here we do the complementary experiment where we ask the question, why do we need the zigzag information at all? What if given a sequence of graphs, I just vectorize the spatial topological information independently and then compare it with ZZ even here, we notice that there's like a clear difference in ZZ performance and what we call the performance as snapshot PH, where we just construct a regular persistent homology at different snapshots. So, which again kind of makes the point clear that we need like a two parameter setup to do this. Yeah, so here, this is a visualization of ZZ vector. So I- so the top row represents samples of label 1 in the finger movements dataset, and the bottom row represents samples of label 0. So you can see that the ZZ Grill signatures look very similar for samples of the same label, but and which look very different from samples of the other label. So this is kind of like some sort of visualization to see, okay, how is CC Grill actually able to capture the differences? Then we report the computation time as well. So it's like one can see from the computation time that the method is actually feasible in practice. So especially the graph method, because point clouds take slightly longer, primarily because the filtration has more kind of simplices. But yeah, but even both the approaches are actually quite feasible. Then further, we also tested the framework on sleep stage detection or sleep stage classification datasets, where the task is to classify whether a person is in the wake stage of the sleep, N1, N2, N3. These are like the three different sleep stages classified by researchers in that field, or the REM stage. So this is like a five-way classification task, and we used ZZ-Grill in conjunction with an existing machine learning model, and we see that it leads to a bump in the overall accuracy and the overall F1 score. So this is again another kind of real world data set that we worked with. So here the signals that we have are the ECG signals from different electrodes placed at different parts of the brain. So yeah. So in summary, we proposed a topological framework for spatiotemporal data, which we call quasi zigzag persistence. Then we introduced ZZ-Grill as a vectorization scheme for extracting topological information from a quasi zigzag persistence module. Then we proposed a way to compute ZZ-Grill using existing zigzag algorithms, and we used the fast zigzag library for this, which is a, a library that they and How have proposed in like 2022, I think. Uh, and then we also empirically validated the claims by experimenting with sleep stage detection datasets and multivariate time series classification benchmarks. All right. Yeah, and thank you for your attention. This was work done at CGTDA group at Purdue, and this is the link to the paper and the code.
Thank you very much. Let's all give Shreyas a round of applause and hope that the Zoom filter doesn't remove it.
Thank you.
Thank you very much. So, do we already have some questions from the audience?
Where's my Zoom window?
Yeah,
Yes.
just speak up. Yeah.
I have one, so I can start.
Sure.
Maybe you said it and missed it, but how many? So this is just for a bifiltration, right? Only if I have 2 parameter. Okay, fantastic. I've been given data that has 7 or 8 parameters. So
Whoa. Okay.
yeah, exactly. But it's okay. We can just choose 2 at the time, which is better than 1. So
Yeah.
okay.
Yeah.
We'll start with 2. But
Yes,
thank you. That's we're gonna try your code, absolutely.
Okay,
Thanks.
cool. Yeah.
And if it helps, you could even project. You could use something like PCA to project to 2 parameters, right? That are combinations of those 7 or 8. But even so, I think this is great. I've been following the grill saga for some time.
Oh yeah,
now.
sorry, I didn't want to come across as only 2 parameter.
No.
It was already very cool.
Yeah, no. I'm just saying, like, you can maybe try it out. Maybe it will give you the right combination of the ones, or you go with subsets. Sorry, that was just me putting on the ML hat. But actually, I had a question.
That's perfect.
Actually, I had a follow up to that somewhat. So, I mean, you now showed this for lots of like time varying problems. Where would you say this could have the biggest impact in terms of like what types of the 2 parameters, what filtration should this be ideally? Because I mean your method is general, right? But like what can you maybe distill your observations to the specific filtrations that are useful in practice?
Yeah, so the method is general for sure, but so the thing is, the one requirement is okay, so this is like a quasi zigzag method. So you have like time varying data. So you have like zigzagging in one direction, and then the other direction. So I primarily, at least for the sake of the paper, I've only worked with alpha filtrations for the spatial scale. But I'm almost, so the other thing is I didn't particularly experiment with, let's say, all these graphics related data sets where they have a lot of very dense point clouds, and then they want to classify an action, right? So yeah, I didn't kind of get to experimenting with that, but that is one place where I see that like something like this can be useful, where you kind of capture the topology of the action, if like quote unquote topology of the action. So yeah, and there again I feel like a regular, so any sort of spatial filtration would be great. But if you already begin with a sequence of graphs, then maybe like an HKS heat kernel signatures filtration
Mhm.
like on the spatial axis might also be quite useful.
Yeah, very. It's a very good point. But yeah, the alpha shapes, of course, as well. Just today or a couple of days ago, like the flood complex paper came out. Maybe that would also be interesting to you. I don't know if you saw that already.
I don't think I have seen it.
Yeah, it's basically
Okay.
a kind of like a mixture between alpha complex meets witness complex meets Viator's ribs. So you get a very sparse simplicial complex that
Okay.
so that Viator's ribs works even even for
Faster.
yeah, even faster, like blazingly fast, and even on the GPU. So maybe that could be something that you might integrate.
Oh, interesting. Okay. So what's the name of the complex? Flood.
It's called the flood complex. I can send the paper to you later on if you want. It's
Okay.
from
Okay.
my
Yeah, that'll be
colleagues
great.
from Austria. So it's
Oh,
the
okay. Nice. Yeah. Yeah, that'll be great. Oh, nice. Okay. Hmm.
yeah. So do we have some other questions from the audience? Yes, please go ahead, Dave.
So my question is, let me apply it to the sleep example.
Mhm.
So you've computed the persistence in this way. If I were studying sleep, I might look for particular patterns
Mhm.
in a time series, which would be used to distinguish what's going on. So right now it's the whole persistence module you're comparing. But as a
Mhm.
scientist, I might say, what is the particular behavior and what does that represent? Have you
Right.
drilling down into that?
Yeah, so not yet. That is actually part of our future work where we kind of track down the representatives for each kind of class and drill down to see, okay, is there anything specific that this representative can kind of is hinting at or giving me? Yeah, that is something that is part of future work. Yeah.
Oh, good. That's
But
good.
thanks for the question. It's like
Yeah,
a
you're welcome.
really nice question.
Thank you.
Mhm.
Right. Any other questions? So one question that I admit I maybe you already said that and I just missed it, but is this more along the line of a feature representation, or is that also at least like can this be made differentiable or like approximated in differentiable fashion?
Correct. Yeah, so that is something that we were also thinking of when we
Hmm.
wrote the paper. Because, okay, to begin with, everything here is happening in the discrete world, like ZZ
Yep.
cross Z. But one could always think of ZZ cross Z being embedded in R3, or rather
Hmm.
R cross R, OP cross R, and
Hmm.
then kind of come up with a way to do this differentiably in R3, and then translate the results back to the discrete world. But yeah, so that was certainly some like an idea that came to our minds, but we have not explored it further yet. Yeah, but it'll
Okay.
be interesting to kind of think about how this can be made differentiable. Yeah, because let's say for the grill framework, it was already sitting in R, so then it was quite easy. But here we need to embed this into R and then do something and then come back. So that's that needs to be
No, no,
carefully managed.
no,
Yeah.
I think it will be challenging, right? So I was just like wondering whether you maybe already had some ideas. It seems to me that the main issue is that everything is being tracked, right? So like things can vanish or cannot vanish, and you have no good way of simply expressing that, I think, in a differentiable fashion. But maybe there's approximations that could be done. I don't know.
Yeah, sure. And especially I think the main kind of issue is the fact that you cannot take epsilon steps in a discrete world, right? So that's the issue. So you cannot take epsilon steps for any small epsilon. So the change it needs to be like a discrete step, and then things might not be continuous or in that step that you take. So that's the major issue that one needs to kind of manage.
Yeah.
Yeah.
Do we have any other questions from the audience? I think it's really nice work to see this now being take shape and form for the for machine learning applications. So that's because previously, like you mentioned Tarkin's theorem, right? And for a long time, this seemed to be the only way to do TDA and time series, if I recall correctly. I mean, I might not be aware of all the approaches there, but now suddenly this comes into play. So one other thing that came to my mind, did you try this already out on some of these time varying graph benchmarks? I think there's now people.
Yeah, so the temporal graph benchmarks, right?
Yeah, the temporal graph benchmark. Yes, of course, yeah.
Correct. Yeah. No, I have not gotten around to trying the method on the TGB yet. And also the other thing is, so this kind of a framework is very well suited for like a graph classification task. So the TGB contains a lot of data sets for node classification or let's say edge link prediction, that sort of a thing. So yeah, so that is something that we also kind of need to think of how to apply this framework for like a link prediction thing, like because this is what we are essentially doing is we are capturing the topological information in a sequence and then using that as the representation for that sequence and using that to primarily do classification. Yeah. So so that was kind of like the motivation for us to choose the multivariate time series classification and show the empirical results on these data sets that okay, like you can capture the representation of an evolving sequence in a specific manner.
Yeah.
Yeah. So that's
really interesting. So I'm very excited about this. I think I will have lots of uses for this method myself. So
nice.
so really
Nice.
thanks a lot. That was really great.
Do you think you can use it also on unclassified data? For example, I'm trying to think about the data that I have, in which it's just a recording of things. So I know nothing about what they are, what they mean, etc. I'm trying to figure it out pattern or the classical TDA. But
I mean, one way that you could potentially do is, let's say, if you have a lot of different like such data samples or recordings, then you could compute the representation and just check how the representations are different for different things. Like instead of looking for the pattern in the data directly, you look for the pattern in the representation of the data.
That is true. That's very clever.
Yeah. Yeah, and then that way the other thing that will kind of enable you to do is use a suite of these machine learning methods that you already have. Because once you have like a representation, then you have a lot of leeway to doing things in and figuring out the pattern in the representations. Yeah.
That makes sense. Thank you.
Right. Any other questions? If not, I would suggest we thank Shreyas again, and we're going to stop the recording and move to the private discussion session potentially. So thanks a lot for being with us today, Shreyas. It was really great.
Thank you.